man with low blood sugar.
So, okay everyone, my name is Tianyi Gu. I'm a fourth-year Ph.D. student working with Professor Wheeler Ruml on artificial intelligence and robotics kind of stuff. And this summer, I'm working in a company called Realtime Robotics. And what they do is they build robotic chips for those robots. And then they try to kind of achieve a fast collision checks time for those robots. And then by the time I arrived at the company, they already launched the first products to those like manipulator companies. So their chips can work in those manipulators with kind of zero out the collision checks times. So make it planning really fast. And then the company also wants to launch their chips to those autonomous vehicle companies to help those companies to build up like fast planners by their chips. So what I'm doing here is working on these autonomous vehicle projects to build up kind of a framework for them to apply their chips on. And then since when I arrived there, they have nothing, so I have to help them to build everything bottom up. So the two basic stuff I do here is to build the online real-time decision-making framework, and also I build a baseline planner for them to compare with their planner, which have the fast collision checker. So to be brief, basically the problem is we have this kind of vehicles drive in urban areas, and then we have a point A and a point B. We want to drive the vehicle from point A to point B without intersect any of the obstacles, the trees, the pedestrians kind of stuff. This is the original problem. And then to solve this problem, of course, we have a bunch of data from those sensors, and then given the data, we're gonna doing plannings on the data. And this is the big picture of how people can solve this. So on the right, we have a bunch of sensors on the cars. So we have cameras, radar, LiDARs, GPS, and then given the data, we can do the perceptions to detect where the obstacle is. And then given the perception, we kind of trying to plan. And then there's kind of 4 levels of plans here. The first is the top route planning, which is kind of like a Google Map plan. So, and then given this plan, we're gonna reasoning about the predictions, which is where the pedestrian is gonna move. What's the future positions of these pedestrians, of this moving around vehicles, and then to predict their movement. And then we come up with this behavior planning, which is basically tell you, okay, am I on a stop sign kind of region, or am I on a highway? So there's different behaviors for the vehicles. And then in the end, we need to come up with the low-level trajectory planning, which we also know as a motion planning. So the detailed motion trajectory of the vehicle. So the company actually focusing on solve this kind of level problems. We need to come up with a low-level trajectory plan. And given the plan, we're gonna send it to the robot. There's a controller take care of that. So here we have a kind of walk through what is the trajectory planning is. So given a city, given a map of the city, and then we assume we already have the high-level plan, which is the Google Map plan, which is a very thin red line here around the city, and then we want the robot to drive from position A to position B. So what we do is we kind of select a temporal goal region inside this high-level plan, and then we know we need to detect where is the current position of the robot is.
Do we want to take a brief pause now?
Sure. Temporal goal region, and then find a trajectory planning, and then tell the robot to follow that plan until we reach the goal. This is how the solution works, right? So these red arrows here are the things we want to focus on, come up with the low-level trajectory planning. So the way we do this is we build up an online real-time framework, which is essentially 4 parts, which is the obstacle tracker to do the perception and then the prediction. And then there's an executive in the middle, which tries to synchronize all the messages and then synchronize the time steps for the plan. And then we also have our planner and then the controller connect to the robot. So what I do there is to build up the executive and build up the planner. And another colleague of is doing the trajectory, is the obstacle tracker and the controller and stuff. So the executive, actually, the essential thing for the executive to do is to do the online real-time plan, which means we want to do the plan while the robot is moving. So what we do is for time step t to time step t plus 1, when we are execute the action AT, we are planning for the action AT plus 1. So we are planning for the AT plus 1 here, parallel with the robot is moving, doing the action AT, right? So this is what the basic thing that the executive is doing. And then I build up this planner, which is called a lattice-based planner, which is essentially I growing a lattice, like online, from the current state of the robot, which action can I take? And then from those, which action can I take? This is kind of a lattice generated online. So the purple squares here are the obstacles, and then this green square is the goal region. Then the red arrows inside are the states, actually trajectories, and then the yellow ones are the states on the frontier, which is essentially on the open list of the A-star algorithm. This is another online lattice I generated, which, as we can see, it's like a stuck inside the goal region. There's something wrong there, but I'm not going to talk about that. So for a lattice-based planner, we need to define what is state, what is the motions. So from a state, we can take a control, which is essentially you turning your wheel and put some gas kind of actions. And then if we take one action, we can end up with an end state. So we call this whole thing a motion. So gives a state, we can have bunch of different actions to take. And then we're gonna select the best end state. From that, we keep growing the motions until we find a state which is the goal state, and then we backtrace all the following trajectories, kind of come up with a plan. And then how to find the best one to do, which we use the A-star algorithm. If you don't know what A-star is, please take the AI class or the mobile robot HO class. They will tell you what's that. So I define my cost function here by, for each motion, what is the cost for each motion, which is the time consumed on the motion, and plus the collision cost. And then the collision cost will be both from the static obstacles, which is the trees or kind of stuff, and then also have dynamic obstacles, which is the peoples and the vehicles. And then I also have to define the heuristic, which I combine the three terms, which is straight path term, velocity term, and orientation term. I'm not going to talk about too much detail, I'm going to save some time. So I also build a collision checker, which check the collision for static obstacle and the dynamic obstacles. But for the dynamic obstacles, we know those kind of belief distributions around each obstacles. So I kind of borrow a formula to come up with the total belief of what's the collide of each motion, of each edge in the graph, if you want to think like that way. So and then the goal checker is actually going to check if the state is inside the goal region and if the velocity is matched the desired velocities. And then based on that, I actually extend this approach to an anytime search, which I modify the goal a little bit. So instead of saying a specific true or false, if its state is a goal or not, I like to return a reward value for each state. If the state is, for example, we want to plan for 5 seconds, that's what we do in the project. So any state achieve the 5 state is a goal state, and it's gonna return a reward as 1. And if it's also not only is a 5-second state, but also achieves and satisfy all the goal conditions, it's what gonna receive a reward like 1,000. So the planner is not gonna stop until it exhausts all the time quota of it. Like we run 10 hertz for the planner in this planner, so you're gonna have 0.1 seconds to do the plan. It's gonna keep planning until it exhausts that 0.1 seconds. And then we're gonna return the solution which has the highest reward.
car is driving at what speed? If it's 1 second for the planner to take the next step.
Okay, so the maximum speed I think is 60 kilometer per hour kind of stuff, which is 30, yeah. No, in the
One
urban,
second was enough.
in the urban area. Yeah,
One
yeah.
second was enough.
And then of course, in the end, the company want to raise up that frequency to like 1,000 hertz to do the plan because of they can zero out the collision check time. And then, okay, so what we do is we don't have any cards, we don't have any hardware. So what we do is we borrow this this simulator, and then doing everything based on the simulator. So. And I built up some visualizers here, as you can visualize the plan. And then the car, this is the simulation system. So the car right now is at the traffic light, and then the right is red. So it's come up with a 5 seconds plan, which is every action is stopped. Because any other action is going to cost you more. So, yeah, and then once it turns green, it will keep coming. You can see this is like one plan, and then it's keep come up with the plan for the next 1 second. I also have some videos to deal with the dynamic obstacles. If you drive in an urban area and then the road looks clear, and then someone just rush into the road behind some obstacle you cannot see, and then the car can trying to reactive that situation, correctly. Okay, that's me. That's my. Thanks. Any questions?